such iconic movie. Me too. Okay, Maxim will talk again about, more about multiple orthogonal polynomials.
Yeah, in spirit, my talk will be related very much to the previous one. So that's why I'm not going to provide the demotivation, because Andrei has done it already. So, well, here we start with the vector of measures. We suppose that all measures are supported on the real line. They have infinitely many points in their support, and they have all finite moments of all orders. So we can compute the polynomial. So in my talk, D will stand for the number of measures. We equip ourselves with the multi-index, which is simply a collection of integers, positive integers. So n1 to nd are essentially the degrees of orthogonalities they're going to later require. Then the multiple orthogonal polynomial, and then, as Andrei mentioned, type 2 multiple orthogonal polynomials P and X, is simply a polynomial of degree. I'm going to call this length X instead of saying L1 norm, where I simply add up all the components of the multi-index n. Is a polynomial of degree at most length n that is orthogonal to all powers of x ranging from 0 to ni minus 1 with respect to the ith measure. So if you have only one measure and you require a full set of degrees of orthogonality going from 1 to n minus 1, however, if you talk about d measures, you split the degrees of orthogonality between those d measures. And as far as the terminology is concerned, if it happens that degree of this polynomial is exactly the length n, then the index is called normal. And if the vector of measures mu is such that all indices are normal, these measures are called perfect. There are two general examples of perfect systems of measures. One, which is known as Angelescu system, is simply the case when all measures are supported on intervals in intervals are disjoint. So let me restate the support of the measure inside of an interval. So delta is the convex whole of the support, and all intervals are disjoint. So delta 1 is here, delta 2, delta 3, delta 4, and so on. Then it's easy to check, exactly as in the classical case, that you need to have exactly n1 zeros, ne zeros on delta e, and therefore the degree of the polynomial will be exactly length n, and that system was perfect. So that paper of Angelescu from 1919 is actually very short, where he verifies that fact. Another system, which is on the other side of the spectrum, which was very complicated, it took a long time to prove, is what's known as the Nikitian system. And it's based, so if in the Angelescu system all the measures had disjoint supports, in Nikitian system all measures are supported on the same interval, and the measures are built in the following way. So what actually Nikitian realizes the following fact: if you have two measures and they're supported on the same interval, what will be important for the asymptotics of the polynomial is the analytic continuation of the ratio of the measures on an interval. So if your measures are absolutely continuous, you take the densities and you take their ratio, and you need to look at the continuation properties of that ratio. And he said, well, let's consider the case when this ratio is in fact a Cauchy transform or a Markov function of another measure. And that's exactly what's written here. So the Nikitian product of measures sigma and nu, it's essentially a measure sigma, but with the weight. And that weight is the Markov function of the measure nu. So you take measure sigma, and you modify it by the weight, which is the Markov function of the other measure. And then you can keep on building in this way. So if you have three measures, the product, Nikitian product of three measures, sigma, nu, and mu, you take the Markov function of mu and use it as modification of the measure nu. Then you take Markov function of that modification and use it as the weight for the measure sigma. So in this case, all the measures are supported on F1, and they all certain modification of the measure sigma 1. So that's the Nikitian system, and it took very long time. So the work of Nikitian was in the 80s, right, Andrei? So it took actually a very long time, for about 30 years, to prove that this system of measures also is perfect. So all the indices are normal, and it finally was done by Guillermo Lopez Algamasina and Ulysses Fidalgo. So this is two examples on the opposite end of the spectrum of systems that are known to be normal. And I don't think there are any other classes of measures actually where we know for sure that all the indices are normal. However, if we know that indices are normal, the multiple orthogonal polynomials, as much as the classical ones, satisfy recurrence relations. So idea is simple. You take a normal index n, so then this polynomial has degree length n, and you multiply it by x. Now it's a polynomial of degree 1 larger, so you would like to expand it in the other orthogonal polynomials. So you need to take a polynomial of degree 1 larger. However, now you have options, right? To increase the degree, you can increase any of the indices of your multi-index by 1, and you can pick any. So you increase the j's index by 1. So this is a monic polynomial. This is also a monic polynomial. Now, in this expansion, the next term, you need to have a polynomial of degree n, and it's exactly Pn, and it comes with certain coefficient that depends on the index n and the index j, the direction into which you increase the index. And after that, all you need to take is all the polynomials of degree 1 less from Pn with coefficients a and I that no longer depend on j. So these coefficients here are actually independent of which direction you took. And there will be no other polynomials. And these are what's known the recurrence relations for multiple orthogonal polynomials. If all n plus ej's are normal, of course, you have all of them there. Well, rather than looking at this as the expansion of x px, you can think of it as the definition of p and j, polynomial p and j. Now you can realize to get to this polynomial from the marginal cases, you can take many different paths. Well, if you want to have a well-defined polynomials, you better have all the paths converging and giving you exactly the same number. So that means the coefficients a and I and b and I in the recurrent relation cannot be absolutely arbitrary. They need to be consistent. Well, and they must satisfy certain relations, and these relations are here on the board. Well, they are what they are. These consistency conditions are there to make sure that if you start building your polynomials out of the marginal cases, you're always going to end up with the same guy here, no matter which path to that index you take. Because all you need to know, right, is the one of the previous indices and indices on one less from that. Notice that in the case d equals to 1, these recurrence relations reduce to usual 3-term recurrence relation for orthogonal polynomials. And I'm simply going to denote b and mu. It's the polynomials orthogonal with respect to measure mu. And it's known in this case that this coefficient is actually positive, so it's more classical to denote it as a n squared rather than a and I as I was doing it here. In fact, as in the classical case, the recurrence coefficients for multiple orthogonal polynomials determine the polynomials and the measures of orthogonality in some sense. So here's the theorem. You take the recurrence coefficients, assume they satisfy the consistency conditions, so you can build your polynomials. And they are such that if you look along one axis, you take the ith standard basis vector, so it has 1 in the ith position and 0s on the other one. You multiply it by integer n, and you look at the ith recurrence coefficient, a recurrence coefficient. That must be positive, and the rest must be 0. And assume also that b and I is different from b and j in this condition. Then, if you take such a system of coefficients, there exists a measure for which these are the recurrence coefficients. And in fact, there's not very complicated result if you have the second part, which is essentially converse, but it says the following. Take measures of orthogonality for your multiple orthogonal polynomials and look at the coefficients from the 3-term recurrence relations of each measure by themselves. Then in fact, what's true about the coefficients of the multiple recurrences is that on the marginals, b e I is exactly bn of the measure mu I, and a n I is exactly a n squared of mu I. And the rest of the recurrence coefficients can be built out of the marginal that you're given here. You can use them as the initial conditions, and then you can use the consistency conditions. You can rewrite them in a way that you can build all other recurrence coefficients based on this ones, so they can uniquely reconstruct them. And then, of course, if you can reconstruct the recurrence coefficient for multiple orthogonal polynomials from these ones, for these ones you can use classical Jacobi operators theory to reconstruct the measure from the recurrence coefficients, right? Because if you have the measure, you know the moments. If you know the moments, you have the polynomials. If you have the polynomials, you have recurrence coefficients, classical ones. If you have recurrence coefficients, you can build the tri-diagonal matrix, which is a Jacobi operator. You can look at the spectral measure, and the spectral measure will be such that it has exactly the same moments of the measure you started with. In particular, if the measure you started with was compactly supported, that's exactly the same measure. Of course, if it's not compactly supported, you can have multiple measures with the same moments. And of course, this basic condition here that B and I must be different from B and J, but in particular, this condition is satisfied as you look for multiple or mid polynomials, as the case of Andrei in the previous talk, or you can look at multiple Laguerre type 1, type 2, or even the orthogonality with respect to discrete measures, Charlier polynomial, or for any Angelesco system. In fact, we can show for any Angelesco system that B and I is always less than B and J when I corresponds to the interval that is to the left of the interval corresponding to J. So now, when you have the recurrence coefficients, you can ask about the ratio asymptotic, which is something kind of Andrei mentioned, but that he needs the boundedness of the zeros to get the boundedness of recurrence coefficients to actually get going through the ratio asymptotics. And here is a result of Wolter-Manasse, which says, assume your indices lie on the restricted ray sequence, which means what? If you take the index n and normalize it by its length, now you got a point in the first quadrant of r-dimensional space of length 1. So let C be such a point, and assume then now that your indices are such that you take C of length 1 in the first quadrant, and well, you multiply it by the integer n, and of course you need to have integers, so you take the floors. And that's the sequence of indices that I call restricted ray sequence. Assume that along the sequence your recurrence coefficients have limit, and you can even allow them to grow, then you can scale them by appropriate power of n, and the power is we're going to call gamma. Then the multiple orthogonal polynomials satisfy this ratio asymptotics locally uniformly away from the real line, where the limit is given by a certain algebraic function. And well, how to find this function? Actually, it satisfies this algebraic equation. So z equal to chi plus, and a's and b's, the sum a over chi minus b, where a's and b's are exactly the limits. In particular, and the branch that you take is such that at infinity it behaves like z. So that would be a function that has d branches, and you would select this one that has unique branch that behaves like z at infinity. In particular, if d is 1, and you assume that an's go to capital A, bn's go to b, this is simply the function z plus b plus square root of z minus b minus 2a, z minus b plus 2a. So if standard normalization b is 0 and a is 1, which is the classical Nevai class, what you get here is z plus square root of z squared minus 1 over 2, which is the conformal map of the minus 1, 1 to the complement of the disk, which is the, again, classical behavior of orthogonal polynomials on the interval. So the question is now, when can we know that the recurrence coefficients have those limits? And since the recurrence coefficients satisfy consistency conditions, it's obvious that you cannot simply prescribe arbitrarily constants A, Ci, B, Ci. So in Nevai class you can, but as soon as you go to multiple polynomials, you cannot. So what kind of groups of constants can actually work out there? So for that, I need to switch from the recurrence relations to potential theory, as Andrei was talking about, because the result in the classical polynomials tells you that if your measure is in the regular class on minus 1, 1, then the zeros of orthogonal polynomials will converge to the equilibrium measure on minus 1, 1. And equilibrium measure is a measure that minimizes logarithmic energy, as Andrei was writing, so that's exactly the right interval to look at. Now, since we talk about multiple orthogonal polynomials, I will need to talk about the vector equilibrium measures as exactly as Andrei was saying, but my setting will be slightly simpler than his. So how do we define vector equilibrium measure? You start with a collection of intervals, fi, and a collection of constants theta I, and a certain of matrix of interaction capital A, where capital A is symmetric and positive definite. You also assume that on the diagonal entries are positive, and Aij are 0 as long as the intervals fi and fj intersect. Then consider the following class of set of vector measures. It consists of vector measures nu, such that the ith component of the measure is supported on the ith interval and has the mass theta I. So what we have here, we prescribe where the supports must be, and here we prescribe the masses. Then you look for the following minimal energy. you take the usual logarithmic energy, mutual energy of two measures, you weight it by Aij, and you take the sum. So again, in the classical case, when you have only one measure, it would be simply the log of 1 over x minus y. Notice I put minus in front. D nu x, d nu y, which is the classical logarithmic energy that Andrei mentioned. And again, it's exactly.
It is only non-intersection intervals.
No, well, if two intervals intersect, this coefficient would be 0.
Well,
Yes.
that's what I'm saying.
Yeah.
So effectively, you have only non-intersection.
But no, but well, only the pairs that do not intersect participate here, right? But I can have 3 intervals, and the middle one intersects the first and the second, right? Then I'm going to have 3 by 3 matrix, and all 3 components will be present in the measure. But as far as the pairwise interactions, only the outer and the leftmost and rightmost will interact, right? And they will not interact with the middle one. So they can intersect, but yeah. It's a matter whether the measures will. I mean, this can be generalized to intersecting intervals as well under other conditions. So then there is a minimal vector equilibrium measure that minimizes this energy. So what you need to have there is the collection of intervals and collective of masses. And now I would like to describe what kind of matrix A in constants you need for both Yattselev and Nikishin system, but I will actually do it in more general case, what's known as a generalized Nikishin system, that are connected with the tree. So I have a tree with the root and d vertices. So I have d plus 1 vertices. One of them is the root that we don't care. And to each vertex, you associate the interval fi, and you put the following assumptions. If vertices are siblings, like in case of v1, v2, or v3, v4, or v5, v6, then intervals must not intersect, and they also must not intersect if the vertices are in the relation child-parent. So they're connected by nature like that. Otherwise, intervals can intersect or coincide any way you like. So that's assumption on the intervals. So intervals do not intersect if the vertices are siblings or connected by nature. Measures. Now, you take any vertex on your tree, and there is a unique path that goes from the root to the vertex. To each vertex, you associate the auxiliary measure sigma I. And then you measure mu n is the Nikishin product of these auxiliary measures along the path that you take from the root to your vertex. So in my case here, well, measures corresponding to v1 and v2 will be simply sigma 1, sigma 2, because the path is actually 1 point. If I go to v3, the path is now v1, v3, so I need to take a Nikishin problem of sigma 1 and sigma 3, which would be a measure supported on f1, exactly as the one for v1, which is sigma 1 modified by the Markov function of sigma 3. And you do it for each possible path on each vertex. So that you got a system of measures for my vector of orthogonality for multiple orthogonal polynomials. And now I need to give you the constant, the masses of my equilibrium measure. And the constant says that. Let's take C of vector of x1 in the first quadrant. This is exactly my direction in which my multiple indices will go. And to each vertex, vi associate the constant ci. Thetas are the following one. You look at the vertex, and then you sum up the constant ci corresponding to the vertex and all its children. So of course, if I had more vertices here, I will take all of them. So notice in this case, when you look at the vertices corresponding to the children of the root, the sum of all of them will be the sum of all ci's, and therefore will be 1. So in particular here, theta 1 plus theta 2 must give me 1. And the matrix, right? Matrix of interaction is the following one. On the diagonal, you put 2. If vertices are siblings, you put 1. If they're connected as a child-parent pair, they're connected by nature, you put -1, and otherwise you take zeros. So what happens here? My Yattselev system is when I have d vertices that are all children of the root. So I have all vertices in the first level, each correspond to the constant ci and the measure mu I in the non-Nikishin products. If every vertex has exactly one child except for the last one, so your graph is simply a line, that's a Nikishin system. And well, for any other tree is what's known as a generalized Nikishin system. And well, according to theorem of Goncharov-Manov, we can formulate the vector equilibrium problem, and we can get a vector equilibrium measure from that. And another theorem of Goncharov-Manov-Sorokin tells the following. Assume that our auxiliary measures are absolutely continuous with respect to Lebesgue measure on interval of I, and the derivative almost everywhere non-vanishing. Take a sequence of multi-indices that goes to this limiting constant C, vector C, and assume that indices for the child are smaller than the indices for the parent. So that's an assumption there. Then the zeros of multiple orthogonal polynomials distribute as the components of vector equilibrium measure corresponding only to the children of the root. And of course, those have the total mass 1, right? Because that's exactly how the constants theta 1, theta 2 will build, because all the C's add up to 1, so all thetas on the first level also add up to 1. Other components of the, so for me in this tree will be imported only omega 1 and omega 2. Other components also have a role, but it's hidden at least from the asymptotics of the zeros of multiple orthogonal polynomials. So that's exactly what Andrei called mu1 and mu2 that were responsible as case for the weak distribution of zeros of multiple orthogonal polynomials. It's also known, at least in the case of Angelescu system, that the vector equilibrium measures are supported on intervals. However, those intervals must be strictly smaller than Fi's, the original one you started. So the measure can be supported inside or pushed to one side or the other. And well, it's probably well known in the Moscow group. This is true for all GN systems, but I spent about half an hour trying to find the paper where it's actually written, and I couldn't. I found papers where it's stated that it's literally said, it's known that this is true, but we're not going to go into details. It's written in that paper. And that's about all I could find. So apparently the general knowledge in some circles that these equilibrium measures are always supported on intervals, but it's hard to find the proof of that claim. Now, so now I know I have my vector measure. I construct multiple orthogonal polynomials. I construct the vector equilibrium measure. I get it supports. It gives me some system of intervals. Through that system of intervals, I can construct my Riemann surface that will be responsible for the function chi that appeared in the ratio asymptotics of multiple orthogonal polynomials. And how you do the asymptotics? Well, as Ken was telling us, you do Riemann-Hilbert analysis. And all I will say about Riemann-Hilbert analysis is the following fact. So first of all, in the classical case of orthogonal polynomials on the line, one-dimensional, the Riemann-Hilbert formulation was derived by Folkashitz and Kitaev, with one of the authors present here. Another one has not arrived yet. But for the multiple orthogonal polynomials, it was it was the generalized to multiple orthogonal polynomials by Geronimo Curles and again Walter von Asse. And it says essentially the following. If your measures are absolutely continuous and the rho i's are the densities supported to intervals, then you can characterize it through d+1 matrix in the following way. Matrix must be analytic away from the real line. It have certain behavior at infinity. So when you normalize it by z to the minus sigma n, where sigma n is exactly depends on your multi-index in the following way. It should have a pole of order length of a and 1, 1 position, and then the zeros of order n1 and 2 and d the other positions. And it also must have a certain jump, and the jump matrix here is simply 1. First row is 1, row 1, row 2, row d, and the rest looks like an identity matrix. So that Riemann-Hilbert problem has a unique solution, and the multiple orthogonal polynomials Pn is actually a 1-1 entry of that matrix. So if you do what Ken told us to do yesterday, you can get the asymptotics of these polynomials if you do all the transformations and to eventually end up with a small norm problem. If you can manage that, you will get the asymptotics of the polynomials. So okay, now I will switch only to Angelescu system. So let me remind what's the setup now. I have a vector, Angelescu vector of measures, which means components mu1, mu d are supported on intervals delta 1, delta 2, delta d. All the intervals are disjoint, and delta 1 is to the left of delta 2 is to the left of delta 3, and so on. I have a direction in which I'm going to take my multi-indices, so my normalized multi-index and will go to the vector C, which has length 1 and lives in the first quadrant in the d-dimensional space. Delta Ci would be the supports of the vector equilibrium measure corresponding to my Angelescu system in my direction C. Rho i's would be the densities, in which I'm going to assume that they are holomorphic functions. And, well, we can do the Fisher-Hartrag, but that's not very important. And by omega n, I will also denote the equilibrium measure that corresponds to the normalized index n. So omega c would be the limiting one, and that would be the one corresponding to the H normalized index. So having those intervals, I can construct the Riemann surface, as Andrei was pointing out before. So except he counts indices as 1, 2 to d plus 1, and I count indices from 0 to d. So that, how do you construct the surface? Well, you take the top sheet, complex plane, you cut along all the supports of the components of the vector equilibrium measure. And notice here I'm actually doing respect to the omega n. So I'm cutting along delta ni, the supports of the vector equilibrium measure corresponding to the normalized index n. Then on the first sheet, you cut only along the first support, on the second sheet, second support, and so on, and then you glue crosswise. That's a surface, and you actually can easily compute that the surface has genus 0. So you can freely prescribe zeros and poles of rational functions on that surface. And what we want phi n would be the one that has a pole of order length of n on the top sheet, and then the 0 of order n1 on the first sheet, 0 of order n2 on the second sheet, at infinities, and so on. That's a rational function, and it's unique up to normalization, so we normalize it in a certain way. Then, if you do Riemann-Hilbert analysis, in this case, you end up with the following result. So you take your Angelescu system, you take your indices, you take the ray sequence, so that normalized indices converge to this vector C. Then orthogonal polynomial is essentially behaves like that function phi n I constructed on the previous slide, modified by a Segue type function, and you need to take the values from the top sheet. And again, Segue type function is nothing else but it's a function that solves a certain boundary value problem on the Riemann surface. And the boundary value problem depends on the weights you have. You solve the problem, you get the function S, and then you take its values from the top sheet, and that's the will give you the strong asymptotic formula for multiple orthogonal polynomials. And of course, if you have strong asymptotics, from that you can deduce the behavior of the Karras coefficient, which will be on the next slide. But before I do that, so that's true for Angelescu system. Such results also were considered for Nikishin systems by, well, none other but Walter von Asche and Lopez Lagamosina. So I feel like this talk is dedicated to Walter. And they did it in the case of d equals to 2, only 2 measures. And for where the limiting constant c must be actually a rational vector with rational coefficients. And I will explain in a second why that was a simplifying assumption. Moreover, so notice that my vector c cannot have components vanishing in this result. In our current work with Aptekarev and Denisov, we actually can get rid of this assumption and can simply assume that you can have marginal sequences as long as all the indices increase to infinity in case of d equals to 2. So you have n1 and 2, and 1 and 2 must go to infinity, but the ratio can go to 0 or 1, or to 0 or infinity. We don't care. We still can do Riemann-Hilbert, and we still can get the asymptotics of the multiple orthogonal polynomials. And of course, there are very many other results on multiple orthogonal polynomials, but most of them are done for diagonal sequences, and I will not mention that. So out of this result, we can get asymptotics of the recurrence coefficients, and I can explain to you what kind of constants A's and B's can appear in Walter's result when he assumed. So as in the previous setting, you have the multiple orthogonal polynomials, you have the index C, you take the vector equilibrium measure, you take the supports of the vector equilibrium measure, you construct the Riemann surface, it has genus 0, therefore it can be conformally mapped onto the sphere. Take the conformal map that has the pole on the top sheet at infinity, and you need to prescribe a 0, but rather than prescribing a 0, we'll prescribe the fact that there are no constant coefficient on the top sheet. That will be my constant chi. It's uniquely determined under these conditions. It must be holomorphic on top of other infinities on other sheets, so it has value b and the constant a coming next to 1 over z. This is exactly the BCI and ACI that appeared in Walter's result, which means for our Angelescu system, the recurrence coefficients have this limit along the ray sequences. So these constants come from a certain conformal map of my Riemann surface onto the sphere. This is exactly function chi, and then of course Walter tells me that I can write an algebraic equation on this chi using ACI and BCI. That's what he did in this result. Moreover, again, the same remark, when d is equal to 2, well, your limiting vector c can be written now as c1 over c, but now this is a scalar. And again, here I have non-marginal cases. We can extend to the marginal situation. We can prove that these constants have a limit when one of the components goes to 0. And then if you look at all marginal sequences that both components in 1 and 2 increase, we still can prove that the recurrence coefficients go to those a's and b's that are limits of a's and b's for non-marginal cases. So now I gave you strong asymptotics. From that I got the recurrence coefficients, and of course now Walter result can tell me the ratio asymptotics, and you can tell me that I'm cheating because strong asymptotics for in one-dimensional case must imply ratio asymptotics, so I proved way more. It's interesting, but it's not immediate that it's actually strong asymptotics imply ratio asymptotics for multiple orthogonal polynomials, and let me explain why. So as I said before, the supports of the equilibrium measures can be smaller than original intervals. So take two Angelescu system on 2 intervals. In fact, what's going to happen, so I can record my direction by this constant c. So when c goes to 0, the support of the equilibrium measure in this interval would be the whole thing, but on this one, it will start to collapse to one point, which is the leftmost point of the interval. On the other hand, when c goes to 1, eventually this measure will be living on the whole interval, but after some time, the support of the equilibrium measure will start to collapse to the rightmost point of this interval. So, and you have two critical case values, when c is small or c is large, where the supports are not exactly the same as the original intervals. So in this case, for different c's, my Riemann surfaces are different. And if you remember, I constructed my Riemann surface, my function phi, with respect to the normalized index n, which means if I change the index, and I'm in the regime when I have the what is called the pushing, when the support is smaller, my surface can change. So if I take the ratio of two phi's, I'm taking the ratio of functions living on different surfaces. And since, of course, if they're genus 0, I could write each of them as the product of simple factors, 1, 1, 0, 1 pole. If they were living on the same surface, I could cancel everything and get chi from there. But since they're functioning on different surfaces, I cannot simply cancel. And it's very non-trivial in this regime to actually go from strong asymptotics to ratio asymptotics. So it's actually a slightly tricky thing. Okay, so at least we can now get the limits for the recurrence coefficients, and then ratio asymptotics and strong asymptotics. What else can you do with this thing? Well, we also can build a theory of Jacobi operators on trees. I kind of quickly mentioned that in one-dimensional case, you take the recurrence coefficients, you put them into tridiagonal matrix. That's what's known as Jacobi matrix. It defines an operator on positive integers, all two of positive integers. And through the spectral measure of this operator, you can recover the measure of orthogonality. And for a long time, people tried to do the same for multiple orthogonal polynomials, try to build the same theory. And in fact, the Jacobi operator that you get is self-adjoint. That's why you can talk about the spectral measure. And the idea was, well, for d equals to 1, you work on the positive integers. So for d equals 2, for example, you need to work on the lattice in the first quadrant. And they couldn't build, Aptekerov tried a lot, and they couldn't build a self-adjoint operator this way. And what happens, the correct generalization, you look at positive integers not like a lattice, but as a tree, where each vertex has exactly one child. And therefore, when you look with d equals to 2, you need to work not on a lattice, but on a tree, where each vertex now, except for each vertex has 2 children. And of course, if you work with d-dimensional multiple orthogonal polynomials, each vertex needs to have d children. Then, well, you define a projection from that tree onto the lattice that I'm going to call pi in the following way. The root corresponds to 1, 1. Then if you move along the left edge, you increase the first index by 1. If you move along the right edge, you increase the second index by 1. And you keep on going this way. So you can see now there are 2 vertices corresponding to the point 2, 2 on the lattice. And of course, if down the tree you go, there will be more and more vertices with the same projection onto the lattice. And again, the same idea. This vertex is the parent of these 2, and those are the children. This is the first child, this is the second. And the function L here determines which child of the parent this vertex is. First, second, and all the way up to D. So that's my tree with the projections. And then on this tree, I'm going to build 2 potential functions. So they have special definition at the root vertex with some freedom of choosing coefficients kappa. But on the rest of the vertices, the potential function y at the vertex y has the following value. You have your coefficients a and I and b and I. You take vertex y, you take its projection of its parent, and then you take an index which child of the parent is vertex x, and then you record that coefficient a as your value of the function ay. And you do the same for b. Now, let's assume the coefficients a and I and b and I such that a and i's are positive and bounded, and b and i's are simply bounded. Again, in particular, if you have an Angelescu system and you take its recurrent coefficients, these conditions will be satisfied. And you define the following operator on a tree. So you take a function f and know 2 of the vertices. So at each vertex has a value, and if you sum them up all, it's in the will be summed up the squares. It will be a finite number, and you define the following operator. You take the value of f at y multiplied by the value of the potential b at y. You take the value of f at the parent and multiply by the square root of the value of a at y, and then you do it the same for all the children. So that's a certain operator on the tree. And it happens that this guy is a self-adjoint bounded operator under this condition on the tree. So when you work with d equals to 1 and you simply live on positive integers, that would be the classical Jacobi matrix that hopefully some of you know. So if you have a self-adjoint operator, you can talk about its spectral measure. And then here we go. Well, that's what Andrei called the Cauchy transform, and people of spectral theory call the Stieltjes transform of a measure. And if you switch the roles z and x, you're going to, the approximation theory is going to call the Markov function. So it has many names. And then the Stieltjes transform of the spectral measure of my Jacobi operator in a tree can be computed through the Stieltjes transform of the measures of orthogonality I started with. In this way, where the kappa 1, kappa 2 were those 2 constants that I had the freedom on choosing the potential b at the root. And what else you need to know? You need to know the difference of the first moment of the measures of orthogonality. And moreover, if the measures mu1 and mu2 are absolutely continuous respectively back, then the spectral measure is also absolutely continuous, and you can compute its density through the densities of mu1 and the Stieltjes transform. And in the other direction, if you know the spectral measure and you know these constants, the difference of the moments of mu1 and mu2, then you can recover the measures of orthogonality. Therefore, you can recover the orthogonal multiple orthogonal polynomials, recurrence coefficients, and your Jacobi operator on the tree. But knowing just the spectral measure is not enough. You need to know this constant as well. And that was all in order to prove this result. Now take this Jacobi operator corresponding to some coefficients I and I, b and I. I'm not saying that they're coming from recurrence relations, simply some. And I would like to know something about the essential spectrum of this operator. Well, assume the following. Assume that a and i's and b and i's have a limit. All race sequences, including the marginal ones, and the limits are a's and b's, and those are not just arbitrary a's and b's, but they're precisely that ones. You take 2 intervals, you take vector c, the limited vector for multi-indices that I used to call, so vector of length 1, and they consider the vector equilibrium problem corresponding to this vector c and Angelescu matrix of interactions. You record the supports of the equilibrium measure, you construct the Riemann surface. On the Riemann surface, you construct function chi, and then you record its expansions at infinities, and you read off the coefficients a and b's. Those, the a and b's, needs to be there. If you your coefficients a and b are such, not necessarily the recurrence coefficients, but any with these limits, then you know that the essential spectrum of this operator is exactly the union of intervals delta 1 and delta 2. So it in some way generalizes the result for classical Jacobi operators. So if you have only one interval, right, they're simply saying that you have limits for a's and b's of your Jacobi operator. Of course, in this case, the essential spectrum is exactly the support of the measure of orthogonality. And now, so in all my cases, I work essentially with Angelescu or Nikishin, and the number of measures of in my vector equilibrium problem was exactly the same as the number for multiple orthogonal polynomials, right? And if you remember anything from Andrei's talk, he had multiple orthogonal polynomials corresponding to d equals 2, but he had 3 components of the vector equilibrium measure. So why that happens? Well, that happens exactly when, and remember he had the situation when the third component disappeared and then the third component appeared. Why that happens? That happens when the supports of the components mu1, mu2 start to intersect, and then you need to formulate a different problem. So let's consider the following system that we call Stahl system. So Angelescu disjoint, Nikishin coincide. Here you have overlapping supports of the measures of orthogonality. So mu1 is supported to -1a, and mu2 supports -ai. We did not want to deal with the potential theory as Andrei did, because remember, Andrei used his potential theory to construct the Riemann surface and to construct, characterize it through a Cauchy transform of the measures from the vector equilibrium problem, and then look at the level lines of a certain differential on the surface. So we start immediately with the surface. And the surface is exactly the same, only he called it psi. And you remember he had the h squared term, but it came with a coefficient which was v prime. We are in unweighted case, so v prime is 0. So the a is simply exactly z squared minus 1, z squared minus a squared. Those are the endpoints of the support. Coefficients next to h is z squared minus p squared, where p is the free parameter. As the case of Andrei, polynomials p0, p1 that were needed to be determined, and the b1 is simply z. And we need to somehow fix the value of this parameter so that my Riemann surface is the correct one for my problem. And you fix it in the following way. Let's take the, so h is a rational function of the surface, so it's you defines a differential. You look at the real part of it, this differential, as Andrei said, and I want this real part of the integral of that h dt to be single valued. So that's what my discussion with him, what I said, are you actually asking for the periods? So this guy will have a periods, right? Because it's on the Riemann surface of general genus. And essentially this condition means we want to choose parameter p such that all the periods are purely imaginary. And in fact, it's possible in our situation. So that's a theorem, again, by Aptekarov, me, and none other than Walter van Asse. And it says the following. If my constant a, so that tells me how deep two intervals penetrate into each other, is less than 1/2 squared of 2, there exists a unique choice of p in this interval such that this condition is satisfied, and my Riemann surface is going to have 8 ramification points. 4 of them are clear at plus minus 1 plus minus a. There will be 2 at plus minus b, where b is between a and p. And there will be also 2 on the imaginary axis, exactly as Andrei had. This is a situation when Andrei had a curve going from one point on the imaginary axis to another. Then there will be a critical case when a equal to the square root of 2. In this case, you have only 4 ramification points. Essentially, b's and a's collapsed. And then when a is bigger, the square root of 2 up to 1, there will be 6 ramification points of plus minus a plus minus b, but the order has changed. And I think that that picture is more explanative than what I just said. So this is the case when a is small. The two intervals do not penetrate each other too much. So this interval, first interval of orthogonality from -1 to a, second one from -a to b. So you get gaps in your Riemann surface here, and there's 2 branch points on the imaginary axis. And here is how we glue the surfaces. So the top sheet R0 has cuts along -1 to -b, -a to a, b to a. The first sheet has cut only from -a to a, and it's glued to the top sheet. And it has cut from IC to -IC, through which it's glued to the second sheet. And the second sheet has cut here, of course, and then cut here and cut there, and through these two cuts, it's glued to the top sheet.
And you will have genus?
2. In this case, it's genus is 2. In this case, to these two cases, genus is 1. So when the penetration is deep, genus becomes 1. So this is the critical one. So all these branch points of order 2, and this one now in the critical case becomes of order 3.
Just curiosity, each of these cases represents sort of different Riemann-Hilbert analysis.
Yes.
And what's the difference in the phenomenon of the zeros of the orthogonal polynomial?
For orthogonal polynomials, not much. Orthogonal polynomial is going to live here, 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 or here, or here, here, here. The difference exactly as in the case appears when you talk about functions of the second kind. If you look at the zeros of the functions of the second kind, they're going to start living in certain curves that I will show you like in 2 slides. So, but in this case, things complicated. You start now do what Aptekarev calls opening global lenses. That's something that you don't have in classical orthogonal polynomials, because you need to move one. You can usually you open lenses only like that, right? Now you're going to have one global lens that you will need to move all the way up there, because the problem will depend only not only jumps here, but also there will be something jumping on this cut.
Are all the zeros living on the real curves, or do some of them live in the complex plane?
In genus 2, there will be 2 rogue zeros, and genus 1 will be 1 rogue zero. Yeah.
Sorry, just one last. Where do the rogue zeros live?
Depends on the periods of a differential, a certain, not all differential, that one from P. If the periods are rational, there will be finite number of points. If they're rationally dependent with constant 1, they'll live on sort of curves. And if they're rationally independent, then they're going to be dense. If you take all of them, they will be dense to the whole surface. Yeah, so that can be wild. So, where was I? So these are how my surfaces are glued. And if you remember now, to describe my polynomials, I will need function phi. Phi is exactly the e to the integral of h. H had purely imaginary periods. So phi is multiplicative, multivalued, but the absolute value is single valued, right? Because all the periods are purely imaginary. It also has a double pole on the top sheet and simple zeros on the first and the second sheet. And in my genus 0 case, I need to take my phi and modify it by what I call Segre type function, which solves a certain boundary value problem on the Riemann surface. I still need to do that, and that's my problem. So the jumps are row 1 when you glue first and top sheet. It's row 2 when you glue the top sheet and the second sheet. And it's a ratio of row 2 to row 1, which must analytically extend to that cut when you glue the second and the first sheets. So it's exactly as a Nikitin. It's important to look at the ratio of the densities from the common part and its analytic continuation properties, and it needs to be nice. So Nikitin assumes that it continues all the way to some interval, and it's actually the Cauchy transformable measure. For us, well, we need to go far enough depending where this cut is. And since it's a higher genus surfaces, as Alexander asked, I cannot simply solve the problem which is not vanishing. I need theta functions. And theta functions will depend on the parameter n, which is exactly the degree here, and they going to have floating zeros. And that's what your question was, those zeros determined by Jacobi inversion problem, and with certain parameters whose rational dependence tell me whether they are finite number of solutions or infinitely many that are dense. And then, well, the result is the following. So psi n, which is the multiplication of phi n with my Segre type function, is describes the asymptotics of the polynomials. You need to be able to normalize, but there are conditions. And the conditions tell me how well something about how far the ratio of the weights must extend. And the case 1, when I had 8 ramification points, they need to extend far enough to cover all bounded components of the regions I, j, k. So what are the regions I, j, k? You take that function phi, constructed as e to the integral of h, and you look where it's a function on the 3-sheeted surface. You take the branches on the I sheets, j sheets, and the k sheet, and you see where the i's value is bigger than the j is bigger than the k's. So again, picture tells me more than that theorem. So in particular, in this region here, the value of phi from the top sheet will be bigger than the value of phi on the second sheet, which will be bigger than the value of phi on the first sheet. And of course, on the top sheet, you expect to be bigger at least at infinity, because at infinity, phi has a top sheet has a pole, and other sheet has zeros. And so at least far away, you expect phi 0 to be always larger. But close to the cuts, things start to change. So in particular here, the second phi on the second sheet is bigger. Here, well, it's the same continuation. And now, answering your question, the zeros of the orthogonal polynomials are going to live here, here, and here. However, if you start taking functions of the second kind, their zero is going to also live on this curve in the complex plane. And this is in case 2, so we need analytic continuation of the ratio to be supported, to be analytic everywhere outside of some compact set here or there. And in case 3, when the penetration of two intervals is deep, in this case, we need to have the ratio that are analytic outside of certain compact set in this hole. And, well, in the case 3b, this hole can completely close in the only case we can handle, and that weights are constant multiples of each other. So when the picture is like that, that's the only thing we can do. And these guys are exactly the trajectories of the differential that Andrei was talking about. Only in our case, they're more complicated than yours. So yours were simply one arc. For us, you can see they form all possible loops that you can have. And I think that's my last slide. Thank you.
So you said that zeros of the function of second kind live on this curve.
Oh,
Zero, this row zero of the polynomial can still be dense.
yeah. Yeah, I mean, so let me restate. If that rock 0 is on the top sheet, it's a 0. It's close to the 0 of the polynomial. If it's on other sheets, it will be close to the 0 of the functions of the second kind. But they're also going to have zeros close to these level lines.
The functions of the second kind, how many zeros do they have?
I will not be able to tell you right now on top of my head. I need to look back.
They scale with n.
Yeah. Yeah, so this is actually, I didn't say it, it's only diagonal sequence, so n that we're treating.
These be used for like computational applications or what?
So Walter tried to do quadrature with multiple orthogonal polynomials, and they're not that great for that.
Okay, but the idea would be you have multiple weights.
Mm-hmm.
Well, one application is
No, I mean, well, yeah, Andrei speaks external source models, right?
Well, I said computation.
Yeah, I mean, so the quadrature formulas, you can use.
So you asked specifically about computation. And what is
So is it possible to have some kind of polynomials which spectral functions are sort of singular, multi-dimensional operator, like Chebyshev or Jacobian polynomials? They have their spectral function is sort of operated in a certain way. Is any analog of that?
Sorry, I don't know.
Well, some of these polynomials are actually eigenfunctions.
Yeah, of this Jacobi that we constructed, yeah.
You could say eigenfunctions. So
They're generalized eigenfunctions, yeah.
this sophisticated Jacobi activity. And also differential equations.
Yeah, differential you can artificially design it, but more interesting applications integral because everything probably
Integrable,
multi-dimensional integral singular equation.
that I don't know.
May I ask a question?
Mm-hmm.
I've never done it myself, so all these trajectories.
Mm-hmm.
So this is a question of some dynamical system, yes? So you study. So how rigorously you draw them?
Oh, this is not rigorous. This is just yeah. This is just a schematic. But no, we do rigorously prove how they look.
But of course you need some just kind of commodity class, yes?
Well, so
you can prove that they don't self-intersect.
yeah. So we use certain conformal map from the 3-sheeted to 2-sheeted surface, and then we use some parameterization to prove the behavior of the trajectories. Yeah. I mean, this is more of an art, right, Andrei, to try to get how the trajectories behave.
You can solve certain differential equations.
Yeah.
I'm just wondering because I'm not an expert, I've never done it myself, so how people, really draw these global pictures.
Well, I mean, it's a differential, right? So you know a local picture, and then you start trying to paste together a global picture and use Teichmuller lemma to say that certain things cannot happen, and then trajectories need to.
Sometimes I understand that there are enough of some general theoretical instrument that could do it. The only problem is that you're dealing all the time with multivariate functions, and none of this, MATLAB, Mathematica, they don't know how to handle multivariate functions. So you have to do kind of analytic simulations. We still need it. Yes.
So maybe it's the same thing, but maybe one of the things that Alexander is driving at is that it's necessary before you can carry out any kind of Riemann-Hilbert analysis to have a complete understanding of these trajectories.
Yeah, because Ken, because right? So in the because no, it's even more, right? When you're Riemann-Hilbert, you need to take the ratios, right, of the phi's from different sheets. So you need to make sure when you open the lenses, those ratios are less than 1. So that's why those omega I, jk are important to us, right? Because it tells you which ratios are small, which ratios are not. Yeah. So yeah, we needed this picture before we can even do Riemann-Hilbert. Yeah.
Thank you again.